Hi, everyone. Welcome to IPAC 2024. Jim and I are very, very happy to start this again this summer. And so today, our series will start off with on the positive formula for Jack polynomials, Jack characters, and the proof of Lassalle conjecture. Am I pronouncing it correctly? All right. So today our host will be Maciej Dołęga. And yeah, so all yours.
Thank you very much. Thank you very much for the invitation. It's a pleasure to be here. So during these lectures, we are going to present a joint result with Hussein Bendali. So that the archive number is here, but maybe I can also add the link to the chat. So this is the paper that we are going to discuss. And here is the plan. So this is a plan for all the lectures. So today I'm planning to present the history of the problem and give you some motivation. And probably that's all what we're going to do today. And then perhaps I will also finish with a quick explanation. What are the main ideas of the proof? And then for the next lecture, we will first prove integrality part of the Lassalle conjecture, which uses slightly different ideas than the positivity. So I will explain what are the main ideas and how you can prove integrality part. And then in the last part of the lectures, and these parts will be presented by Hussein, he will talk about the positivity and also about the combinatorial, the main combinatorial objects that we are counting in our formula, which are maps, which are graphs drawn on the surfaces. Okay, so let me start. So let me start with the definition of Jack polynomials. So Jack polynomials, these are symmetric polynomials. We will actually talk about symmetric functions. So there are symmetric functions, and they have also this extra parameter alpha. So you can think about it as a formal parameter, and there is this standard definition which is given by three conditions, namely the unitriangularity in the monomial basis, the fact that they are orthogonal, and the normalization. So there exists a unique family of symmetric functions So they are indexed by partitions lambda. They have this extra parameter alpha such that three conditions are satisfied. So the first condition is that J lambda is always expressed in the monomial basis such that the expression involves only smaller elements than lambda in the lexicographic order. And these guys here, there are some coefficients, so they belong to the rational functions in our parameter alpha over Q. The second condition tells us that this family is orthogonal. So the scalar product is always equal to 0, except when lambda is equal to mu. When lambda is equal to mu, and this is given by some number. And then the third condition tells us what is the normalization that we're working with. So the first two conditions, they already almost uniquely gives us this basis, except that we need to choose some normalization. And the normalization that we're going to work with is given by this formula that if you look at the coefficients of the monomial indexed by the partition, by the trivial partition 1, 1, 1, 1, 1, this coefficient is simply given by the size of your, the degree of your polynomial, lambda factorial. So the way to think about it is that Jack polynomials can be obtained by essentially by Gram-Schmidt orthogonalization process applied to the monomial basis. So it's a quite abstract definition. So maybe there is not much that you can see about them from this definition. So let me show you some examples. Just to finish my definition, I should also define my scalar product. I didn't tell you what is the definition of the scalar product. And the definition is an alpha deformation of a classical scalar product on the ring of symmetric functions. So one way to define it is to define it for the power sum basis, such that the power sum basis is again orthogonal. And when we have two power sums indexed by the same partition, then their scalar product is equal to this formula. So if we will not have this parameter here, namely if alpha is equal to 1, this is just a classical scalar product that we're using when we're working with symmetric functions. So this is basically how you define Schur symmetric function, again up to normalization. And the difference between Schur symmetric functions and Jack is that you have this deformation here. So you deform your scalar product. So for instance, when alpha is equal to 1, then your Jack symmetric functions are equal precisely to Schur symmetric functions up to an explicit normalization factor, which is just a hook product. So this is this is a classical formula that also tells you that you can think that Jack polynomials is some kind of one parameter deformation of Schur symmetric functions. And there is some other special case which is of interest from representation theory point of view, namely when alpha is equal to 2, then it turns out that that the Jack are equal to so-called zonal polynomials. So for people with representation theoretical background, zonal polynomials are spherical functions. So these are spherical functions for the Gelfand pair GLN ON, where ON is an orthogonal subgroup into GLN. And then finally, for people who are familiar with McDonald polynomials, you can also obtain Jack polynomials as a certain non-trivial limit of McDonald. So what you do, you take an integral version of the McDonald polynomials with Q equal to 2 to the power alpha and T, and you divide them by 1 minus T to the degree. So if you take an integral version of McDonald polynomials and you take this specialization, then after taking the limit, you obtain precisely Jack polynomials. So this is the definition of the main actor in this talk. And here is the problem that we would like to address. So the problem is find a formula for Jack symmetric functions in the power sum basis. So let me start from this very special case when alpha is equal to 1. So I will try to solve this problem when alpha is equal to 1. And the solution is given by Young's formula. So there is a theorem which was proved originally by Young. And the formula looks like that. So let's T be any bijective filling of a Young diagram, lambda by numbers 1, 2, up to the size of lambda. And then you could prove using Young's result that J lambda at alpha equal to 1 is given by the following formula. So we sum over two permutations. The first permutation belongs to the column stabilizer of our filling T. And the second permutation, it belongs to the row stabilizer of the filling T. And then we take a sign. So a sign depends on the parity of the first permutation. And the associated power sum is the power sum which is indexed by a cycle type of a product of these two permutations. Okay? So we take sigma 1 times, we take sigma, this white dot times sigma black dot. We look at this permutation. We look at the cycle type of this permutation, and this is precisely the index of the power sum. So this is a very, very nice formula, a really beautiful formula. And then you can try to think, is it possible that this formula has a really straightforward generalization to arbitrary alpha? So if you think that this is a formula that is a special case of some yet unknown formula that works for alpha equal 1, maybe you can propose something very simple. So the wishful thinking approach would suggest the following formula. So maybe it's true that there exists some statistic which is defined on pairs of permutations such that if I basically copy my formula, but now I put arbitrary alpha, I can write it like that. So here everything would be exactly the same. But now instead of taking -1 to the sign, I would like to multiply it by alpha to the statistic. There's a question mark because we don't know if this is true, and that was a first guess, which was given by Hanlon, and Hanlon wrote a conjecture that there exists a statistic such that such a formula holds true. So my personal opinion is that it actually might be true by coincidence. So what does it mean? It means that if you think about this formula, how it works, even for alpha equal 1, this is a formula that involves many, many objects, but at the same time, it also involves many cancellations. So this means that you sum over a big object, a big number of combinatorial objects, but many of them are canceling out each other. So it might be possible that there exists some function on pairs of permutations such that indeed such a formula is true. But when I say that it might be true by coincidence, I mean that maybe there is not any meaningful statistics on pairs of permutations that has some kind of nice combinatorial interpretation. So, you know, if you think about all possible functions defined on pairs of permutations into integers, it's a huge family of functions. It might be possible that there are so many terms canceling in this formula that you might find a function that satisfies this formula. But I personally do not believe that you can find a statistic which has some kind of combinatorial meaning. So this is just a side remark, but this is a side remark which comes from the fact that maybe there is a different type of generalization of the formula. So maybe this generalization is not the best one. And when you start to think about different connections between Jack polynomials and other areas of mathematics, you might have some kind of impression that you can find a different type of generalization of the formula that from combinatorial point of view has somehow bigger chance to work. So this is exactly where am I going now. So the first kind of important thing is that we would like to propose some kind of change of the parameter that is supposed to give us some kind of combinatorial meaning. So instead of keeping alpha as the main parameter that should potentially give us some kind of combinatorial meaning, we would like to propose to use this very small change of this variable, which is simply just shifting by 1. And let me tell you, where does it come from? So one important connection between Jack polynomials and other areas of mathematics is a connection with statistical physics. And if you're working with random matrices, there is a very well-known model of random matrices, which is called Gaussian beta ensembles. This model has two important submodels. One which corresponds to Gaussian unitary ensembles, and another one which corresponds to Gaussian orthogonal ensembles. And there is a very well-known technique in random matrix theory that whenever you are trying to compute some quantities related to random matrices, so for instance, you want to take an integral of some quantity with respect to your probability measure related to random matrices, you can expand it as a formal power series of the inverse of n, where n is the size of your matrix. And this expansion involves some discrete topological objects. So these discrete topological objects are graphs which are drawn on surfaces. And it turns out that when you're working with the unitary group, then you obtain only orientable surfaces. And when you work with the orthogonal group, then you obtain both orientable and non-orientable surfaces. And the relation between these unitary and orthogonal cases to alpha is that one corresponds to alpha equal to 1, and another one corresponds to alpha equal to 2. So this change of variable that we have here, it essentially tells you that when alpha is equal to 1, this parameter b is going to disappear. So perhaps what we are really counting here, maybe we are counting some kind of graphs drawn on surfaces such that when b is equal to 0, which corresponds to alpha equal to 1, we just kill all the non-orientable surfaces. But when b is equal to 1, so alpha is equal to 2, then we also have this extra non-orientable surfaces. So of course, again, this is somehow wishful thinking, because the problem that we are looking at is quite different, and so far it has nothing to do with random matrices. But this is some kind of insight that we can take from random matrix. And it turned out that actually this insight really works. So let me show you how the formula that I just showed you actually is related to counting these graphs on surfaces. So now let me introduce maps, the main combinatorial object that we're going to work with. So this is going to be a very quick introduction, but I think that in the future, when Hussein is going to be a host, he will probably give you much more detailed introduction to maps. So, but right now I'm gonna be brief. So a map is a graph embedded in a surface such that it cuts the surface into polygons. So let me show you an example. So the first example, so suppose that I have two polygons, actually two triangles. And one thing I can do, I can glue their edges like that. So what's going to happen with these two polygons when I glue their edges? So topologically, what I will get, I will get a sphere, and the image of these three edges, it will look like that. So for instance, here, the interior of this face, it corresponds to the first triangle, and everything that I have outside, so everything here, it also topologically looks like a triangle, and this is the second triangle. So this is exactly what I mean when I say that we draw a graph on a surface, but I draw it in this specific way that when I cut this surface along these edges, I obtain a collection of polygons. So here is another example. This is a fairly standard example because probably the first time you saw a torus in your life, you also saw this picture. So if you take a rectangle and you glue the opposite edges such that these arrows preserve their direction, what you get a torus. But what I care about mostly is the image of these four edges. So when I glue these four edges, I obtain two edges, and one edge, it will be this kind of circle on the torus, and the second edge, it will be this circle. So this is another example of a map. So this map has only one face because it after destroying my surface by cutting it along this graph, I obtain only one polygon. So it means that it has only one face, and it has two edges and one vertex. Okay, so this map has three vertices. It has two edges, two faces. One face here and one face here, and three edges. And it's a planar map. So whenever I have a map which is embedded into a sphere, I will call it planar. And this is a map which is drawn on a torus. It has precisely two edges. So this is one edge, and this is another edge. It has only one vertex, and it has also only one face because everything here is simply connected, and you can see it on this picture because everything here is just the interior of this polygon. Okay. So we call a map bipartite if the underlying graph is bipartite. So this means that we can color its vertices using two colors, black and white. And black vertices are connected only to white vertices, and white vertices only to black vertices. And a map is labeled if the edges are labeled by the consecutive numbers, 1, 2, up to n. So here is a fact, a very important fact that is gonna show us that actually the formula that I showed you, the formula which is coming from the work of Young, can be reinterpreted as a formula that is counting certain maps. So the fact tells us that labeled bipartite orientable maps are in a bijection with pairs of two permutations of the same size. So let me give you this bijection by showing an example. So first of all, I would also like to draw some Young diagram with a fixed filling, because then I want to use these two permutations from the column stabilizer of this filling and from the row stabilizer. So let me just take this Young diagram, and let's sigma white vertex is given by 1, 4, 2, 3, and 5. And the second permutation, 1, 3, 2, and 4, 5. So you can see that the first permutation stabilizes columns, and the second one stabilizes rows. So they are chosen exactly the same as in my previous formula. And then how this bijection works. So first, what I do, I just draw each vertex per each cycle. So for the first permutation, I will draw 4 vertices. And I will also add some very small half edges. The number of half edges is equal to the length of the cycle. So I have 4 cycles here. I'm also counting fixed points as cycles. There are cycles of length 1. So for the first one, I put these labels to these half edges, 1, 4, 2, 3, and 5. And I do exactly the same thing for the black vertices. And here is where the orientability comes from. So the orientability comes from the fact that I need to fix some orientation such that when I'm adding these numbers to these half edges, I'm going to follow my fixed orientation. So suppose that I fix my orientation to be a clockwise orientation. So this means that if I put 1 here, then I should put 3 and 2, and not the other direction, not the other orientation. So you couldn't see it for the white vertices because each of them had only 2 or 1 half edge. But whenever you have 3 or more, then it really matters. So next, what I do, next I just connect these half edges whenever they have the same label. So if I do this, I obtain a picture that looks like that. So in this very particular case, the graph that I obtained is actually a tree, which means that it is embedded into a sphere, into the sphere. It has only one face because, you know, I can just walk around it and I explore the whole graph. But you can imagine that it can be much more complicated. So the picture can be, it can look like this is not going to be bipartite, but this is because I want to be quick, but it can have some kind of non-visible intersection on a plane, which essentially means that we are on a surface which is not the sphere any longer, because you cannot just draw it without a intersection on the plane. So, you know, it can be a pretty complicated picture, which looks like that. This is just example that I have chosen is relatively simple. So this graph is just a tree and it lives on the sphere. But also you can see easily that you can invert this. So if you start with a bipartite map on any orientable surfaces, which is labeled, then you can just construct these two permutations. And the last important thing is that actually the structure of this map, it encodes the product of these two permutations. So how does it work? It works in the following way. So if I want to understand the product of sigma white vertex, sigma black vertex. So suppose I'm gonna check what is happening with 1. So 1 is sent to 3 by the first permutation, and then 3 is not sent to anything. Let me try to check what is happening by looking at this picture. So this means that if I'm looking at 1, my picture tells me that if I follow it like that, then 1 is transferred into 3 by the black permutation, and then 3 goes to 3 by the white permutation. So it means that actually this walk that I told you that corresponds to faces, if I will walk around this map, then I can actually completely understand how this product looks like. So let's just check. What should I do? I should just check. I should just read every second label. So 1 is sent to 3. I don't read this 3. And then it's sent to 3 again. And then I read this 3. So it means that 1 goes to 3. Then 3 goes to 1. I don't read it. Then it goes it goes to 2. Then it goes to 2. So it goes to 2. And so on. So 2 goes to 1. 1 goes to 4. And then finally, 4 goes to 5. 5 goes to 5. So I put 5. And if you have a more complicated topological object, you just read these labels the same way inside of each phase. And this means that actually each phase of this map corresponds precisely to a cycle of the product. So finally, let me translate this condition that these guys are row and column stabilizers. So how one can think about it? One can think about it in the following way. So suppose that I have my Young diagram that I have started from, and now I know that I will use some colors. So now I know that my black vertices, they correspond to some permutations that are stabilizing rows. So it means that actually each black vertex belongs to some row. So in this example, this vertex here, it is a permutation 1, 2, 3. So we can see that it belongs to the first row. So I can indicate it like that. And then my second black vertex, it corresponds to the second row. So I can actually encode it by adding some extra labels to these black vertices. So I can just add these labels 1 and 2. 1 means that this black vertex should go to the first row. And then this 2 means that this black vertex should go to the second row. And now I can do exactly the same thing with white vertices. So now white vertices, they represent some column stabilizers. So this means that they should be sent to some columns. So, for instance, this guy should go to the first, sorry, to the third column. This guy goes to the second column. This guy goes to the first column, and the last guy, it goes to the second column again. So what does it mean? What did I just do? I just said that actually the formula that I showed you can be reinterpreted in a completely different language. And you can say that you sum over all embeddings of maps into Young diagrams. So basically, when you sum over this pair of permutations, because of the bijection that I told you, this means that you're summing over maps. But there's this extra condition that these permutation, they should belong to the row and column stabilizers. But I just translated this into embedding such a map into my Young diagram. So this point of view is kind of completely new, even though this is just a translation of the original formula of Young. It brings a lot of new information. And in particular, it was absolutely crucial to prove a conjecture that was given by Stanley and some bound for the characters of irreducible representations of the symmetric group. And the insight actually comes from one new information. So in this picture, I was looking at some embeddings which are injective. But actually you can write the same formula using all the possible embeddings of the map into Young diagram. So not only injective, but all the possible ones. So what does it mean? It means that if I first decide to which rows the black vertices are going, then whenever I have some white vertex, the white vertex can go to actually almost any row, except that it cannot go to some row such that if I will look at the XY coordinate, it will be outside of my Young diagram. So what does it mean? It means that, for instance, if I look at this vertex, it is connected to a black vertex which goes to the first row. So this means that this white vertex can actually go to any place here. So maybe here, maybe here. But if I will look at this vertex here actually cannot go, it cannot go here. And it cannot go here because it is also connected to this vertex, which is telling me that I will have a point here, and the point here is outside of my Young diagram. So one can translate this condition by saying that actually the label of white vertices, if I choose this label to be the minimum of the labels of black vertices, so here it's 1, here it's 1. Sorry, the maximum, I'm sorry, the maximum. So here it's 2 and here it's 2. This actually means that each of these white vertices can go to any box which has coordinate from 1 to lambda I. So in other terms, I would just write the formula. I'll just write a formula which is a non-injective version of the previous formula. And this formula is a theorem of Ferret and Schneider. So suppose that I have a Young diagram lambda of size n, and then I can write that for alpha equal to 1, this normalized Schur polynomial is given by the following formula. So this is a sum over all maps. So what kind of maps? So these are just labeled, orientable, and bipartite. maps. And then I sum over all colorings of the black vertices by numbers from 1 to the number of rows of my Young diagram. So if you remember the previous picture, I was choosing each black vertex to be sent to one of the rows. So this coloring tells me which row did I choose. And then what I have here, I will have a power sum indexed by a partition, which is a face type of my map. So by face type, I mean I'm looking at all the faces of my map, and I'm also looking at their degree. So if I look at the degrees of all the faces, this gives me a partition. So this is the partition that gives me my power sum. And finally, I have a product over all I. Maybe I will take this part to the next line because I don't have space here. Minus lambda I to the number of the white vertices which have label I, and I just recall that the label of the white vertex is the maximum of the labels of the black vertices. So I label only black vertices, and then the white vertices, they somehow they inherit a label from black vertices by looking at the maximum among all the black vertices which are connected. So this theorem actually tells us several things. So the first thing is that it tells us that the Young formula that I showed you in terms of tableau and some permutations can be completely rewritten as a sum over some maps. And moreover, it has this kind of very nice feature that once you have this formula, you can kind of understand what is happening when the Young diagram lambda is quite large. If you choose to look at the coefficients of P indexed by some fixed partition, and then you add many fixed points. So this type of problem is actually a problem about the asymptotic behavior of the irreducible characters of the symmetric group. And in general, it's a really, really difficult problem because all the classical tools that we have to compute characters like Murnaghan-Nakayama rule, or even the rule that I just showed you, the one which comes from Young, they're extremely inefficient when your symmetric group is very large. So if you're trying to say something about the asymptotics, all the classical tools are completely useless. And the power of this theorem is that you replace this injective embeddings by non-injective embeddings, and then you can see that somehow you have a lot of freedom to choose where these white vertices are going to go. And this was a very crucial theorem to prove some very non-trivial bound for the irreducible characters of the symmetric group. So now once we have this formula, I'm ready to state the main conjecture. So the main conjecture, which is Lassalle's conjecture. So first, what Lassalle did, he defined the following quantity. So essentially, this is just a coefficients of the power sum for Jack polynomials, but the difference comes precisely from this point of view of the asymptotic. So now mu and lambda, they do not have to be of the same size. So it is going to be a function on the set of Young diagrams. This is one way to think about it, which has this property that if my Young diagram lambda is small, this is just 0. So if the size of lambda is smaller than mu, this is just 0. But if the size of lambda is large, then I will have some normalization factor. So the normalization factor is maybe not extremely important right now. I will just write everything. But what you're looking at the coefficient of the power sum in your Jag. This is for lambda greater or equal to mu. So this is, in some way, it's like a generalization of just the coefficient of power sums for the same size as the Jag that we are looking at. So it has this property that that this quantity behaves extremely nicely from asymptotic point of view. So one way to think about it is that if you again think about alpha equal to 1, this is some sort of normalized irreducible character of the symmetric group, and it tells you what is the value of this character for arbitrary irreducible representation given by lambda. So lambda can be very, very large. And what is the value of this character on a permutation that has a very small support. So essentially you just fix the support of your permutation and then add a lot of fixed points because you want to look at very large representations. So now there is a comment that essentially what Farrah-Stanley formula tells you is that for alpha equal 1, this quantity is, roughly speaking, this is just the number of embeddings of bipartite maps with phase type given by my partition mu. So remember that I think about this quantity that mu is fixed. So it's a small map. And I'm trying to count in how many ways I can embed all the bipartite orientable maps with this fixed phase type into this very, very large Young diagram lambda. So this is more or less the insight that comes from the formula of Ferry and Stanley, Ferry and Śniady. And then we're almost ready to state Lassalle's conjecture. So in order to state it, we want to encode Young diagrams in a quite unusual way. So we are going to use something which is called a multi-rectangular coordinates. So whenever I have lambda, I'm going to encode my lambda by two sequences of numbers. So the first sequence, it's going to be a non-increasing sequence of non-negative integers. And the second sequence is going to be a sequence of just of integers, of non-negative integers. And how does it work? So basically, this is called multi-rectangular coordinates because I would like to draw my Young diagram as a collection of rectangles. So whenever I have a Young diagram, I can represent it as a collection of rectangles. Oh, okay. Sorry, my drawing is not perfect. So R's are height of these rectangles, and S's are length of these rectangles. And one very important remark is that This representation is obviously not unique. So I can represent a Young diagram using these R's and S's in many different ways. So for example, just look at this very simple example. So if I take lambda equal to 5, 5, 4, 2, 1, 1, so maybe the most canonical way to represent it. So let me just add that I will use this convention that if I use this multi-rectangular coordinates, I'll just write lambda is equal to s to power r. So to power r. So maybe the most classical is that I just kind of divided into these rectangles by looking what are the distinct numbers here. So I have 5, I have 4, I have 2, and I have 1. So this means that I have 2 5s, I have 1 4, I have 1 2, and then I have two 1s. But of course, I can also use a completely trivial representation. So I can just write 5 5 4 2 1 1, and then I can take all the r's equal to 1. And so on. And you can imagine that I can do it in many different ways. I can also choose some r's equal to 0, so which basically means that I don't have such a rectangle. So you see that there are many choices to encode Young diagram using these multi-rectangular coordinates. But what is quite surprising is that you can actually find some universal formula that simultaneously work for all the possible representations of your Young diagrams. So here is a conjecture of Lassalle. This conjecture says that if we look at the -1 the power mu times z mu, so this is just a normalization factor, times our generalized character that we call Jack character. And then we write it using this multi-rectangular coordinates, so s's and r's. Then there is some kind of universal polynomial that works for all lambdas. By all lambdas, I mean if I choose s's and r's being equal to specific numbers that represents a specific Young diagram lambda, then I obtain a formula for my Jack characters. And this universal polynomial is a polynomial in B. So remember that B, this is this parameter alpha -1 minus S1 minus S2, etc. R1, R2, etc. with non-negative integer coefficients. So this is really remarkable because it actually means that there is some kind of universal polynomial that simultaneously work for all lambdas. So it really somehow doesn't depend on lambda. And on top of that, it has this extremely nice algebraic structure. So it has coefficients that are just non-negative integers. So let me just go back to this case alpha equal to 1 that we mostly discussed. So for alpha equal to 1, this conjecture, it corresponds to a conjecture of Stanley. So Stanley conjectured such a phenomenon for irreducible characters of the symmetric group. And this was proved, first it was proved by Valentin Ferret. And then the formula that I showed you the formula of Perez-Śniady, it implies this conjecture almost immediately. And this is because if you think, again, if you think about these embeddings, this formula basically tells you that you sum over all maps, and then you embed the vertices of your map into this kind of rectangular pieces of your Young diagram. So in fact, it gives you an explicit formula for this polynomial. When alpha is equal to 2, then actually a similar formula then the formula that I showed you, the formula of Ferre and Śniady, was also proven by Ferre and Śniady. And now this formula involves orientable and non-orientable maps. So in particular, we proved a little bit later that this conjecture of Lassalle for alpha equal to also works. But now the question is, what about this general alpha? So the biggest problem is that these two cases, alpha equal to 1 and alpha equal to 2, we know how to handle them because we have representation theory. So for alpha equal to 1, we have a representation theory which is related to the symmetric group. For alpha equal to 2, we have a representation theory which is related to the certain Gelfand part of the Gelfand pair of the symmetric group and the hyperoctahedral subgroup. So you can use this representation to kind of, again, naturally interpret non-orientable maps using matchings. But now when you're working with arbitrary alpha, all these tools basically disappear. So it's really not clear what to do. And the main result that we're going to discuss during these lectures is that actually we managed to prove the conjecture of Lassalle, and we also managed to find an explicit formula. So I should finish now. Is it okay if I will talk for maybe like 5 more minutes, or is it better that I will stop now and continue next week? Okay.
Yeah. Exactly.
So okay. So I just need to add to give you one definition. I will try to be quick. So I need to define something which is called a k-layered map. In fact, I kind of secretly already gave this definition, but now let me be a little bit more precise. So now my map can be either orientable or non-orientable. And I will say that a map is k-layered if, first of all, I can decompose a set of black vertices into some layers. So I will have like k layers, and similarly, white vertices are also given by these layers. So think of these layers as these labels that I was talking about. So the layers basically should tell you to which row of the Young diagram we're gonna embed our map. So we have this condition that whenever I have a white vertex with layer I, then first of all, there exists some black vertex in layer I such that these two guys are connected. And second of all, whenever something is connected to this vertex, then it is in the layer which is at most I. So this corresponds to this condition that I was telling you about before, that I'm kind of taking the maximum of the black labels for the white vertices. So this is the first condition, and the second condition is that I just need a notation. So whenever I have a partition So this is a partition of the degrees of all the vertices in, sorry, this is I. Of all the vertices, black vertices in a layer number I. So then additionally, I will say that a k-layered map is labeled if, first of all, for every j, if I look at the set of all black vertices in the ith layer, such that their degree is equal to j, then this set is labeled by numbers 1, 2, etc., up to mj of my partition. And then second of all, for any vertex, for any black vertex, each vertex has a rooted oriented corner associated with it. So let me just make a quick picture with an example, and then I will state the theorem, and then I will finish. So first I need to draw some bipartite map. Okay. And now, so the first thing is that I need to put some layers. So let's say that this vertex has number 1, this vertex has number 2, this is in layer 2, and this is in layer 2. So this is two-layered map. So now my second condition essentially tells you that the white vertices need to take the maximum of their neighbors. But this is like you don't really need to add it because it comes directly from the definition. And then because I will have in layer 2, I will have some vertices that have the same degree. So for instance, this vertex has degree 4. Sorry, this vertex has degree 2, and this vertex has also degree 2. So this means that I need to label them. So let's say that this is the first one, and this is the second one. And the final condition also tells me that I need to orient some corners around the black vertices. So maybe here I orient a corner like that. Maybe here I orient a corner like that. Here like that, and here like that. So these are basically the objects that we are going to count. These are our k-layered labeled maps. And theorem number 1, it says that this jagged character is given by the following formula. So it's -1 to the size for partition mu, and then we sum over all layered maps. So this infinity here means that I don't specify k. So they are k layered for some k, such that their phase type is given by mu. And then I have my parameter p to some exponent, which is some statistic on my maps, divided by 2 to the number of black vertices minus the number of connected components times alpha to the number of connected components times, and I will continue in the next line, a product from 1 equal to 1 minus alpha lambda I to the number of the white vertices in ith layer divided by this combinatorial normalization. So this theorem is a straightforward generalization of the previous theorems that work for alpha equal to 1 and for alpha equal to 1 for alpha equal to 2. And a direct consequence is that we have a formula for Jack. So this is theorem 2. We have a direct formula for Jacks. So we can write that the Jack polynomial is minus 1 to the power n sum over all over all layered maps, such that the power sum is given by the phase type of our map. And then this whole factor here basically should be copied into this formula. And then finally, the third theorem is that Lassalle's conjecture is true. So I'm really sorry for being over time. Just quickly, I just want to say that this was like an introduction to what we are going to talk about in details. So next time I'm going to explain how to prove the integrality part in Lassalle's conjecture, because it's a bit different than the positivity. So the positivity part, it comes directly from theorem 1. So the Lassalle conjecture, theorem 1 implies positivity part immediately. Integrality is proven using completely different kind of combinatorial tools. And then in the last part of the lectures, we will explain how to prove theorem 1. So I'm really sorry for being over time.
No, you're
thank you for
fine.
listening.
Thank you so much. That's so great. So, any questions? I actually have have several, but so the very first one is that there are the representation of the rows that you mentioned before, like it's not unique, right? But if you so is there a reason why we allow the S to be weakly decreasing but not strictly? Would that be unique?
So, but somehow, yes, I mean, but the point, somehow the point is different here. So the point is that actually there is this unique polynomial that simultaneously work for all the possible representations. So this is maybe the most surprising fact. So in particular, of course, you can stick to this unique representation, but the conjecture says that for the unique representation it's going to work, but actually it's going to work for all the other representations.
Even more.
Yeah,
I see.
Exactly. So this is something highly, I would say it's surprising. I mean, once you know the formula, the combinatorial formula, this is not that surprising. But if you don't know the combinatorial formula, this phenomenon is surprising.
I see. Okay. Yeah. The other question that I actually have was like I think I missed something when you were going through the example. So if you can go back to
Sure.
when you were trying to write the the example that we have, kind of like the reverse of having the graph. Yes, exactly this one. So I think, is there like, how did you know where to put the blue arrows in the first place? Like, yeah, so like I understand that the 1 and the 2, then you just fix the row, but then afterwards, how am I going to read it back?
Sure, yes. So that's a good question. So yeah, I was maybe a little bit quick about it, but I think one way to think about it is the following. So if you know that each white vertex corresponds to a cycle, and then you know also that each cycle has to correspond to some of the column in your Young diagram, because this is my condition that I have chosen sigma white vertex to be a column stabilizer. So if it's a column stabilizer, this means that each cycle has to be associated to one of the columns. Okay. So that's exactly what I did. So then I said, and exactly the same thing with the rows, right? So the black vertices, they correspond to the cycles of the second permutation. Each cycle corresponds to precisely one row because it's an element from the row stabilizer. So now what you wanna say is that you send black vertices into rows and you send white vertices into columns, but you do it in a way that if you look at the intersection of them, this should be a box which is inside of our Young diagram. So another way to think about it is that each edge is sent directly to a box. So this is clear because each edge is labeled by a number. I first labeled my boxes in my Young diagram by the same numbers. So each edge go to a box, but each edge has two ends, black end and white end. So then you can think that one of these ends is like X coordinate and the other end is Y coordinate of this box. So the original formula of Young is this injective embedding, which means that each edge can go to unique box and each other edge cannot go to the same box. But imagine that you want to now ask yourself what is happening if you will look at all the possible embeddings of edges into the boxes, such that possibly the same box will be occupied by several edges. And then I translated this into this condition that I first choose a row for the black boxes. And once I have chosen all these rows, then the white vertex can go pretty much everywhere, but it cannot go, it cannot go too far right. And this too far right translates into looking at the maximum label of the black vertices and choosing the row which has the index given by this maximum.
I see. Okay, so that just means that like if we have the graph and then have like, if I give you the graph, there are actually multiple because it's an injection, not a bijection. But is it correct? Okay, I see.
Yes. So I mean, so essentially, why this is good to work with this injection, with these other embeddings, is that then you can work with really large Young diagrams, and it's somehow easy to look at the asymptotics which comes from this formula. So asymptotically, this formula will tell you that there will be like a dominant part which is coming from planar terms, and it looks like a volume of a certain polytope. But yeah, I don't want to go too much into details about it.
Yeah, I understand. Thank you so much. Any other questions? All right. So if not, then let's thank the speaker again. All right. So we'll see everyone on Thursday.